Hey algebra friends, let's go ahead and move on to 5.2 notes, day 2. We're going to finish talking about rational exponents, and we're going to move some of these radical functions onto the coordinate plane to see what they look like on the coordinate plane and really talk about domain. So remember, domain is your x values. We're going to talk about that in a second. I'm going to share my screen and we're going to go over our notes for today. So let me pull up my notes page here. And we're going to just finish talking about rational exponents. So remember that when I have a rational exponents, these are the same thing. I can rewrite my rational exponent as a radical form by taking the denominator here. The denominator is going to be your index or your root, right? So same thing here. If I have a to the m divided by n power, then it's the same as a to the 1 divided by n power raised to the m power. And just like we talked about last time, that denominator comes to the front and it becomes your root. So this is what we call the nth root. This is the nth root of a raised to the m power, okay? So this is it written out, skipping the middle step there. A to the m divided by n power is written in radical form as the nth root of a raised to the m power, okay? So let's try some down here. We did some together. The 7th root of 15 to the 1 power. I'm saying 1, that's our understood value, right? If I don't have an exponent, then my exponent is understood as 1. So I have 15, take my root here, it's my denominator, raised to the 1/7 power. So 15 to the 1/7 power. Let's do another one. 18, the cubed root of 18 to the 4th power is the same thing as 18 to the 4/3 power. Same thing. Let's look at this one. I don't have a number here, so I know it's my understood square root, right? Just like the one over here, it's understood square root. My 2 comes over here, and it's x raised to the 5/2 power, okay? We're going to talk about this a little bit today because we can solve for this value here. We can simplify it even further by doing this. And I want to bring you back to like simplifying radicals. Remember in geometry when we simplified radicals, let's say that I have the square root of 18. I know that 18 is not a perfect square, but I can simplify it by pulling out perfect squares. So we can rewrite this as 9 times 2, right? And 9 is a perfect square. So it is the cubed root, or 3 times the square root of 2, right? We can do the same thing here. If I have the square root of x to the 5th, and I'm going to teach you a couple of different ways today, I can write this also as, let's see, how many squares, x squareds, are in here? I have 2x squareds and an x to the 1 power, right? So I have 2x squareds that I can pull out. Yeah, oh, sorry. The square root of x squared is x. I can have 2 x's that I can pull out and another x that stays in. I was moving ahead of myself. So my answer here is x squared times the square root of x. Simplified, right? Simplify. So our answer there that we had at the beginning, x to the 5/2 power, we can also use our division skills here and simplify this, this fraction. 5 divided by 2 is 2, so 2 come out. And there's 1 left over, right? Square root of x. Or think about it like this. You have 2 wholes and 1/2, right? Same thing. Same thing, yeah. So we're going to do some more of those. A little bit tricky, but I really love radicals because we can use our exponent rules all over the place here. Let's look at this one. T times the cubed root of t to the 6th power. I'm going to teach you 3 different ways now because sometimes I need to see it visually. Let's see what this looks like. If I write this out, this is the same as me saying t times t times t times t times t. Is that right? Yep. And I'm looking for groups of 3. How many groups of 3 can I find? I found 2 groups of 3. So I can pull 2 t's out of the radical. And so don't forget that t guy out here, he's out there. So I have t cubed as my answer, right? Let's look at it a little bit differently. If I wrote this as a rational exponent, I can say this is t to the 6/3 power. If I divide here, that's t squared, right? T squared. Same thing, t cubed. We can also look for perfect cubes. So if I have t times the cubed root of t to the 6th, let's write this out. How many perfect cubes do I have? I have t cubed times t cubed. I have 2, right? So don't forget the guy outside. Times t squared, t cubed. Same answer, 3 different methods. Your choice. However it works best for you. If you're a more visual person like me, sometimes I need this, right? If you like to work with the fractions and divide, you can use that. If you want to find the perfect squares or cubes or roots or whatever, you can use that method. Same answer anytime. So let's move to the next one. I have the square root of x divided by the square root of x cubed. So I'm looking for perfect squares. Well, I don't have a perfect square on the top, but I do have x squared times x on the bottom. So I can pull out an x here. So I have x here, then I have an x, square root of x. Simplified even further is 1, right? So 1 over x. So that's my answer. I can do the same thing if you're choosing to divide. I'm going to move this up so we can see the whole whiteboard. So if I change this to a fraction, rational exponent 1/2 divided by x to the 3/2, remember your quotient rule, we can subtract 1/2 minus 3/2. Oh, that's pretty ugly, isn't it? -2/2. What do we do with negative exponents, because this is x to the -2/2 or to the -1, right? It goes to the denominator, so 1 over x to the 1, or you can just leave it 1 over x. Both ways work. Both ways work. All right, let's do another one. Let's do 39. This is 39. I have z squared times the square root of y to the 5th times z to the 4th. So we're looking for squares, right? Let's write this all out. This is when writing it all out can kind of become a headache because we have 5 y's and 4 z's. That can become kind of complicated, but sometimes it helps. I'm looking for square roots. I'm looking for pairs. This is how I like to think about it too, especially if I'm looking for a square root. In a square root, you have to find 2, right? So I need a partner to go on a date, right? I need somebody else to go on a date with me. So if I don't have a partner, I can't go to the dance. So I know that's silly to think about, but that helps me remember it, right? So I have a pair here, so I can pull out 2 y's and I can pull out 2 z's, and lonely little y has to stay inside for the date. So what do I have on the outside? I have 2 y's and I have 3 z's and a square root of y. That's how you'll simplify there. We can also do it other methods if you want to divide. So I have z squared times y to the 5/2 times z to the 4/2, right? If we divide here, well, this wasn't under the radical, so it stays outside anyway. 5 divided by 2 is 2 with 1 left, right? 1 left inside. And 4 divided by 2 is 2, so those come out. So I have z to the 4th, y squared, z to the 4th, y radical stays in. That's that way you can divide it. Same answer, same answer. All right, let's do another one. Let's do x times root x divided by x cubed. This is number 40. If I write this all out, I have x times root x all divided by 3x's. Remember, I'm looking for pairs because it's square root. So I'm going to pull out a pair and one stays inside. He's lonely. He doesn't have a date. He's got to stay inside. Any number over itself, ooh, they're 1. Don't you love that when answers become 1? Love it. Whatever method suits you, it'll work anyway, I promise. Let's do number 42. I have x to the 3/5 power raised to the 2/3 power. This is your power to a power rule. When we have power to a power rule, we're going to be multiplying, right? Multiply. So I'm going to multiply my exponents. 3/5 times 2/3. 3 times 2 is 6. 5 times 3 is 15. You can always reduce. Anytime you get a fraction, you can reduce 2/5 here. So I have x raised to the 2/5 power. I can't reduce this, right? But if I rewrite it in radical form, it's 5 times x squared. Now, since it's fifth root, I have to find a group of 5. Well, I have to find a group of 5. Maybe you're looking for a group discount. 5 people going to the game or something. I don't have a group of 5, so I can't go. So my answer stays here, just like that. Okay. You can change those to radicals if you want to and find groups that way. Let's do 43. That one looks, let's do 44. This one looks pretty gross. Because we have a plus sign, that makes everything just really confusing, right? This is the 4th root of x plus y. All right, if I think about this in roots, this is the 4th root of x plus y cubed divided by the 4th root of x plus y. So think about this written out. This is x plus y, x plus y, x plus y, right? And they're all 4th root. Well, I know that they can cancel like that. That's really nice when things are being multiplied and they look the same. They look the same in the parentheses. They have the same sign and they're being multiplied. So I can cancel them and they have the same root. So what do I have? I have the 4th root of x plus y and I have 2 of them. So it's squared. Nothing on the bottom. That's your answer. We can do this by subtracting 2. We have that x plus y raised to the 3/4 power in the numerator. And if I change this to a rational exponent, it's 1/4, right? So when we subtract our exponent, because it's our quotient rule, I'm always following the math rules. You got to follow the algebra rules. If you don't, you never know where you'll end up. 3/4 minus 1/4. So I have 2/4. So x plus y, 2/4, same thing, get the same answer, the 4th root of x plus y squared. Same answer, 2 different methods. All right, let's move on. Let's do 45 because that one's kind of tricky and then we'll go to domain. This is the square root of the cubed root of x. This is kind of like my parentheses, so I'm going to move out as we go, okay? So the cubed root of x, I'm going to take that. This is to the 1 power. So I'm going to say this is 1/3, right? So this is the square root of x to the 1/3 power. Since it's square root, it's raised to the 1/2 power, right? So when I have a, this is another power to a power rule. So when we have a power to a power, we're going to multiply. So when I multiply 1/3 times 1/2 straight across, so I have x to the 1/6 power. That's an okay answer. Rewritten in radical form is the 6th root of x. Beautiful, right? Beautiful. All right, let's flip to the back. I want to talk about the domain of a radical function. So think we've been talking about radicals and exponents. You can rewrite them as each other. And you have some rules here. And I'm going to show you why these rules are what they are. So my rule here is if n is odd, the domain of f of x equals nth root of x is the set of all real numbers. So if this number is odd, think about 3, 5, 7, ... right? All the odd numbers. Then your domain, remember what domain is. Domain is your set of x values. I'm going to write that here. Your set of x values. Okay, if n is odd, then your domain is a set of all real numbers. And I want us to think about that, because if I have cubed root, remember when we talked about cubed root? If you have a cubed root, it can be negative or positive under there, right? So if I have cubed root of 8, then that's 2, right? And I can also have the cubed root of -8, that's -2. It can be positive or negative. But remember when we had the square root of 4, that was positive or -2, but I can't have the square root of -4, that was positive or -2 with an imaginary number, right? This is imaginary, so it's not real. That's all that means. It's not real, not real. Okay, so we're gonna look at this on the graph and see why. But let's read this one first. If n is even, so that means that if your root is even, like 2, 4, 6, 8, and so on, then then your domain is a set of all non-negative. What does non-negative mean? Non-negative means that it can't be a negative number. So can't be negative. And it has to be greater than or equal to 0. That's what non-negative is, right? Greater than or equal to 0. That means whatever's under the radical can't be negative. All right, let's see what this means. Let's look at this on Desmos. I'm going to stop sharing here. And I'm going to share my Desmos calculator. And I'm going to show you this. Very interesting. All right, so let's look at our x squared. This is my x squared. Let's get rid of that. This is my function of x squared. So f of x equals x squared. See how my x values, they're paired with positive y values. So positive x values, positive y values. So any number that's x here has to be a positive number, right? Can't be negative. The outcome of this root has to be positive, okay? All right, so let's look at what that looks like for cubed roots. Use my fancy things here. These are just my parent functions. It's going to change once we put numbers in here, but these are just my parent functions. So look at our cubed root. See how every x value, even if the x value is negative, it matches with a y value. So this is all real numbers, all real numbers. Let's see if I put a 5 here, what happens? What happens when I put a 5 here? Bam. Same thing, all real numbers, right? Looking at the graph. It's just that we're hugging closer to the y-axis. So let me exit out of this one. Let's see what happens if I put a 4. Oh, look at that. 4 still has to be greater than 0. So my outcome of my expression has to be greater than 0, right? Okay, so let's think about what this looks like for algebraically, and how we can find the domain algebraically. So I'm going to exit out of that. I'm going to put my square root function here again, because we're going to come back to this. I love using Desmos, so easy. Okay, so let's look at our first one, right? G of x equals the square root of 6 minus x. So what do I know? I know that if it's even 2, 4, 6, 8, which it is, it's the square root, right? The outcome of this expression has to be greater than or equal to 0. So what values can I put under the radical or in plugging in for x that makes this greater than or equal to 0? So I'm going to subtract 6 and solve just like we usually do, right? Then I'm going to divide by -1. Remember that funky inequality rule? When you divide or multiply by -1, you have to switch the sign. I totally forget that all the time. So x has to be less than or equal to 6, okay? X has to be less than or equal to 6, or it's going to be imaginary. It's not going to be real. Okay, so let's look at what this looks like on the graph. Share your decimals. Here we go. And you can test these out. Just test out your numbers. So my function is 6 minus x, right? Whoa, look at that. So we're proving ourselves right because all of my x values are less than 6. Interesting. All of my x values are less than 6. Now, why does it point this way? It's because my x value under here is negative, but that's neither here nor there. We'll learn about that more as we go. I just want you to know how to solve for that domain if it's even, if your root is even. Okay, so I'll stop sharing that. So we proved ourselves right. That's good to know. Go back here. So if I have the 4th root of x, I know that my x value, the outcome of this, has to be greater than or equal to 0. Oh, well, I've already solved it. And we already saw that one on the Desmos, so that's good. And then we have the cubed root of x minus 6. Well, since it's cubed, we're going to follow our rule up here because it's odd, so it's the set of all real numbers. So let's look at this on the graph and see if we're correct. Flipping back and forth. All right, so let's see. Oops, okay. Let me share it. There we go. All right, get my functions out. Go to n, so I have the cubed root of x minus 6. Look at that. It is true. It's all real numbers. What happened though? It just moved over, right? Interesting, but it's at +6. So think about that. We have to flip it, right? Okay, so that kind of proves what our domains are as far as radical functions. We're going to do some more of these in class, but take a look at your homework first. Get your questions ready. We do have a quiz coming up, so be ready for that. And I will see you next time in class. Bye.